You are watching the webcast live. That's what you're doing. Sorry for the blurriness. Thanks so much for inviting me. I'm very happy to be here, and I think D3R is an amazing resource, and I hope it continues to grow. And I'm really happy to be here to share more deep learning approaches for structure-based drug design, where of course the goal is to do virtual screening or lead optimization, and as part of that, you need to do post-prediction, binding discrimination, affinity prediction, where post-prediction, affinity prediction is what we evaluated in D3R. And the key subroutine when doing that, as you all know, is protein-ligand scoring. Giving a snapshot of a ligand and a receptor and complex gives some score for how good that is. And a conventional scoring function is something like AutoDoc-Vina, which is what we use for our baseline. Is a bunch of pairwise potentials, steric, hydrophobic hydrogen bond is shown here, and you just add them up and you get your score. And what we'd like to do is do something better because there's so much data out there. There's hundreds of millions of bioactivities in PubChem. Most of them are inactivities, but there's still data. Hundreds of thousands of structure in PDB, and even when you take the intersection, you're left with tens of thousands of annotated complexes. And we like to shove that all through a machine learning workflow. This is my slide that describes all of machine learning. You put features into a black box model and you get some prediction. Right? And for us, our model is going to be neural networks, which are just a collection of neurons, which are nonlinear functions that take inputs and produce an output. And the key thing you need to know about this is how general they are. You can prove that they can approximate any continuous function over a bounded domain. So this is a very general nonlinear model. In particular, we're going to apply deep learning. All deep learning is a neural network with multiple layers, with the hope that by having multiple layers, successive layers can learn higher order abstractions. Right? There's a lot of hype around deep learning, which should probably make you suspicious, but it's also been very successful, right? We can now beat the world's best player at Go, and not by a little bit. It's not even funny how well deep learning can play Go. Speech recognition is all in our house spying us. This picture in the upper right, I took this in Pittsburgh. On the right here is BSD3. This is my office right here. On the left here is an Uber self-driving car. You can see the sensors on top, right? We have these going all around Pittsburgh. Right now they have a driver and an engineer in the front seat. Starting next year, supposedly, they're going to have no one in the front seat, which is both scary and exciting. It's probably more exciting if it's not happening in your city. But all of this is powered by deep learning. How does this work? It is through by just training, machine learning training. You show it examples and it develops a network to make the right predictions. So with a neural network, you show an example, you push it through the network, you get some prediction, you compare it to the known label and calculate some loss. And the key mathematical underpinnings of deep learning is this backpropagation algorithm, which tells you mathematically how to assign blame for that loss to each component of that network, each weight, every parameter. Right? And this is going to come back to us in a little bit. One particularly successful application is image recognition. You all know this on Facebook, you can recognize faces and all this stuff. And there's been this competition going on every year for recognizing images. So you show the computer picture and it says it's a dog, it's a cat, it's a Winston Terrier or whatever. And starting in 2012, this convolutional neural network deep learning approach has just sort of gone better and better to the point where it's claimed is as good as or better than humans. And what is a convolutional neural network? Well, it's a neural network where instead of taking all the inputs in a neuron, you just look at a tiny piece of the image. This is a convolutional filter, and compute some function of that and put that out into an output feature map. And what this does is maintain the spatial relationships of these features so that you can then learn higher order spatial features. And also there's weight sharing, and the other key aspect is that the input is the image itself. You don't have to decompose it into features. And what for images, an example of hand-tuned convolutional filters are like this, where you can recognize edges going top to bottom, left to right, or in any direction. Right? And when you actually train convolutional networks on images, they learn filters that look an awful like these filters that are known from signal processing, in addition to ones that no one has any idea what they're doing. And so if you think about 3D structure design, right? you have spatial relationships, and you can imagine learning local features such as a hydrogen bond, a van der Waals contact, and then you can imagine combining those into higher order features such as hydrophobic enclosure. And so our goal is to learn CNNs that do this for protein ligand scoring, so we can do all these tasks. How do we do this? Well, instead of having an image of 2D pixels with red, green, blue values, we just have a 3D image of voxels where instead of red, green, blue, you have carbon, nitrogen, oxygen. So some representation of the atom density at that point in 3D space. And that's it. There's no additional featurization other than you pick a grid resolution, density, and what atom types you care about. And for training data, we use the PDB bind. We're using the refined set for the models I'm showing here, so about 4,000 complexes. Importantly, we're using docked poses, right? We don't want to learn a model that distinguishes between a crystal pose and a docked pose. We want to learn something that distinguishes between low RMSD docked poses to high RMSD poses, because that's what we want to evaluate. And for affinity prediction, we can just use those poses and use the assigned affinity and predict that in a regression. This is the actual model used for this particular exercise. We have 3 layers of pooling and convolution. At the end, there are 2 separate fully connected layers that take the output of all of these convolutions and in theory represent higher order features that are summarizing this 3D scene. And one of them makes an affinity prediction, a number, a PK value, and the other produces a probability that this is a low RMSD pose. So that goes from 0 to 1. So we have 2 actual scores for every run through the network. Here are some retrospective results. This is training on PDB refined and testing on CSAR. So this is not my normal rigorous attempt to evaluate the generalizability of the model because CSAR and PDB overlap. I'm putting it here because I think this may actually be more representative of how you would use these things in practice, where whatever target you're addressing may have a lot of homologs in the PDB. So you can see we're doing much better than Dino on the same sets of poses. This is just an AUC showing that we're picking out lower or enriching for low RMSD poses. This is the affinity prediction. It's the scatter plot's kind of a mess, but the RMSD and correlations much better. For if I were to actually do clustered cross validation where your test set is very different than the training set, then the RMSD would go up to about 1.7-ish. But so we're doing pretty well for scoring. But we really want to go beyond scoring. And this is where we revisit backpropagation. Right? So backpropagation, remember you assign the blame to loss to the parameters of the network. Imagine you have a network you trust, you believe it's correct. We aren't going to change the network. Instead, we're going to keep going with that algorithm and change the input. So we're using the network to tell us how to change the input so we get a better score. And when you do this in images, you get something like this. You get a noisy image and you optimize for a certain class and you get this result image. All right, audience participation time. What class is this optimizing for? Bananas. Someone actually said it. For some reason, everyone is hesitant to say it, but thank you. It's bananas, right? You're not bananas, it's bananas. You probably all were thinking bananas, right? Yeah. But when you look at that, there is not a picture of a banana there. Right? There's some essence of banana, long, elongated yellow, but that is not a picture. You would not eat that. And this is the problem we're facing is when we backpropagate, we get something like this that says, okay, in this region, I want more oxygen here. In this region, I want less oxygen here. But this isn't fully physical. In fact, if you look at that ligand carefully, it's saying, I want less oxygen in a place where the ligand doesn't actually have any oxygen to begin with. Kind of hard to make that ligand. However, if we keep backpropagating from the grid onto the atoms themselves, we can turn these into gradients, into direction gradients, saying, here's how to move the existing molecule. So you're keeping the whole molecule the way it is, physically, chemically tractable. And all you're using the network is to say how to move it around. Right? So obviously, you're going to move those oxygens closer to that arginine. Right? And so we can do this to, I call it energy minimizing, refine, pose optimizing a pose. Right? And so this is the very first move I made. And this is not buggy, it is actually improving the score. But watch very carefully, hopefully it works. Here's what happens. Right? So it actually pulls that molecule in, and it's now clashing with the receptor. In fact, it knows that part that Clash is bad. You can see it from the red, but it's still has a better score because what it did is it made these electrostatic contacts, and it just emphasized those more. And the issue here is in our training set, we had no physically gross examples, right? They're all docked models. There's nothing where the ligand was completely overlapping the receptor. It was never taught how to properly balance between a steric clash and a favorable electrostatic interaction. And this is an example we're minimizing. We have a bunch of poses that are all low MRSD, and we're going to, and if we can properly optimize them to do the true crystal pose, then you would have that gray distribution, right? But when we take this model and optimize them, almost all of them get worse. So we're not going in the right direction. So the minimizing, it's just not working. And I had to cherry pick this because it's so cute. This was actually an example where it did work, where we took a high RMSD pose and made it a low RMSD pose. So watch this. This is super fun. All right. Let's see your physics-based scoring function do this. Right? It spun around right through the protein and got to the correct RMSD. Now, I tweeted these slides before I started talking, and someone already started complaining about these and said that, oh, actually, it could be in either position, 180 degrees flipped. Look, they actually pulled up the electron density. But let's just trust the crystal poses for this example. But obviously, there's something wrong from the terms of physics and how it did that. So going back to these poses right here that we generated are exactly the most informative poses, right? They're the ones where the model is confidently wrong. And we don't really want to reward people for being confidently wrong, especially not in elections, although that has happened, I understand. And so we want to penalize them. So we throw these back in the training set and say, no, these are wrong. And then that shifts this whole left. And it doesn't shift it all the way to the gray, unfortunately, but it's going in the right direction. And so now we have a clash-sensitive model, and this is what we used for D3R. And if we revisit this example, it no longer spins around, which maybe you're more comfortable with, but on the flip side, we didn't get the right answer. So this is something that we're thinking about, is there some way we can have the best of both worlds? But this is what is used for D3R. Just out of curiosity, anyone here use Venus, Mina, Nina? One, a few. Okay, so this is how docking works there. You just have some Monte Carlo chains where, unlike with ICM, the ligand's part of the sampling, and you're just going along, and you're using a grid accelerated Venus scoring function to select the best poses. And if you ever wonder what the exhaustiveness parameter is in any of these, it's just setting the number of these chains. And then from those best poses, you do this final refinement. And this is where, for the D3R, we inserted the CNN refinement. You do the CNN refinement or the VNA refinement. And then from those poses, optionally, we could also do rescoring. So you could refine with VNA and then to rescore that exact pose with the CNN and so on. So here's how we did. We were not red, that's for sure. So for cathepsin, we were kind of, it wasn't so great. We were right in the middle. I'm going to explain which green dots are which in a little bit, and you'll see why this is the case. But for many of the other ones, we were close to the top. We weren't the top, which was nice. I don't know why. For P38, we had the distinction of being the worst, and one of them we really did poorly. But for the other ones, we're up there, which is nice. Never number one, which is not nice, but many of these were within the error bars of number one. And so when we actually look at the data, and this is Spearman, I kind of agree, I like Spearman, I understand it. So for cathepsin and P38A, forget them, we did poorly, but for the other ones, we did respectively, I think. And the other key trend to note here is the model, CM model that is trained for affinity is the one that's winning. So we trained for a task, we did well on that task, which makes sense. Whereas the other, the training for scoring didn't really work so well for affinity. And Able one, we just didn't have our act together. We didn't actually submit it, but we did do it like a day after the deadline. So you won't see this on the website, but there's the data. Now for post prediction, it's flipped. The model that's trained for scoring actually did better than the model that's trained for affinities used to suspect or hope. And VINA is in between. But we're improving on VINA. Of course, these are all horrible for the reasons that were discussed. My philosophy in these challenges is you take the input, you do it, you don't pull in any other information. I want to evaluate the tool for what it's doing without throwing in anything else. I don't know if that's a good philosophy or not. It certainly doesn't get you to the left of this graph. But this isn't very useful because there's so many bad poses. If I pull these out, this is showing the number of compounds that are less than the RMSD on the x-axis. So you can see for the first phase, whereas cross-docking is basically a wash, but for phase 1b, whereas redocking, we did at least get some low RMSD poses. And what's nice is for the low RMSD poses, the CNN scoring actually did, if we sampled them, this isn't across the top 5 we submitted, this is across all the ones we generated. If we sampled them, we picked out the low RMSD poses, which is nice. And of course, once you get higher RMSD poses, you know, who cares if you select them or not. And so we're doing better than VINA, but the affinity model doesn't work for post-selection. So that'd be a great place to end, because what happened here is in all of these challenges where we did anything, we did better than VINA. In the past challenges, we didn't do better than VINA. But as I was coming over on the plane, they have wireless on the plane, so I started working on this, and I took our existing models and applied to the exact same poses we submitted to challenge 1 and 2. And in the interest of full disclosure, here it is. We did not improve on challenge 1. We did not improve on challenge 2. I was very tempted to remove these slides from the talk. Oh well. So for the future, we want to change that. One of the advantages of D3R, in addition to the blind challenges, it's this accumulating set of data that you can keep using, and we will keep using it as we use CSAR. And so we have a lot of ideas how to improve this. We're not done yet. And I want to acknowledge especially Jocelyn, who is a MOLSI, is that how it's pronounced? MOLSI fellow now, who did a lot of the grunt work of this task. And Josh and Matt were very instrumental in the CNN, and I have a great group now. And funding, you know, if it wasn't for NIGMS, I would not be here at all. So I'm very appreciative of that. And I'd be happy to take any questions. Oh, everything is free, open source, GitHub, and I have Twitter. So there you go. Thank you.
Not
maybe, but so for challenge 2 is FXR, and we actually did this thing where we tried to make an FXR specific model, and it did worse than the general models. So we didn't try it again this time because of that. Maybe we should have.
I'm curious as to whether you could, there's been a lot of work on adversarial networks.
Oh yeah.
I mean, it seems like this would be a really natural application for that sort of work.
Oh yeah, we're working on it. Yeah, in auto, all the cool stuff. There's lots of stuff to do here.
Did you find evidence that you're sampling local things quite well? I've been blinding, you showed a little bit of that, and then also hydrophobic enclosure, things like that.
Right. So how do you turn these statistical models into a physical model, or vice versa, right? And so the way we do that is we look at the filters. And so I can tell you, so these are the low-level filters. Some of these I can point to, and I can say this is identifying a polar interaction. It'll probably take me more time to explain this map than I have. But there's other ones that I can point to and say I have no idea what this is doing, which is similar to the image recognition problem. You can point to this and say this is very much like an edge recognition filter, but I don't know what this is. No. This is not my laptop, so I won't take it. Yeah.